So, in the last session, we had studied about the ZENOR diode. So, what do you mean by ZENOR diode? We'll quickly revise it and then we will look into what is a ZENOR diode with load and without load. So, it is a heavily doped semiconductor diode which is designed to operate in reverse direction and is known as ZENOR diode. It usually has two breakdowns, that is avalanche breakdown and a Zener breakdown. So we had discussed this in the previous class. So what do you mean by Zener diode as a voltage regulator? You can see the diagram here. So diagram here. So we are giving an unregulated voltage, that is Vi. It is given with respect to a limiting resistance Rs. This is your Zener diode, and the current which is flowing across the Zener diode will be Iz, and IL will be the current, and that will be flowed across the load resistance. So output what you get will be regulated voltage. In the above figure, a circuit limiting resistor Rs, as I had said you, is included in series with the source voltage Vi, and the Zener diode to limit the current through the diode to a safe value. The maximum current in the circuit is given by Vz divided by Pz. So this is an important formula which you need to know. So Pz is given by power rating of the Zener and Vz is given by Zener breakdown voltage. When the input voltage Vi is less than the Zener breakdown voltage Vz, the diode does not conduct. Output flows through the input. Follows the input. I repeat it. The diode does not conduct and output follows the input. However, when the input voltage exceeds Vz, the breakdown occurs and voltage across the output remains constant at Vz. So first of all, what do you mean by voltage regulator? We have discussed all these things in the previous class. So regulator means which it means to regulate your output voltage. If there is any variation in the input, but still your output should be constant. For that purpose, we do use a Zener diode. So we are using a Zener diode here, limiting volt resistor, and we are once it crosses a breakdown voltage, then the output remains constant. Okay. So coming into Zener with load, you can see Zener with no load. Sorry, I repeated, Zener with no load. Previously, what did we study? Zener with load. Here, Zener with no load. Okay, no load. So what? Same diagram. We don't have a load. That's it. So input Vi, Ri is a limiting resistor. This is your Zener. The current which is flowing across this will be Iz. Okay, the output is nothing but your Vz. Vi is an unregulated DC voltage. Vz will be the constant voltage what we get. When the reverse voltage is applied to a Zener diode equals to the breakdown voltage Vz, Zener breakdown occurs and Iz flows through it. Applying KVL to the loop, Vi minus of Iz R1 minus of Vz is equal to 0. Iz is equal to, just equated, Iz is equal to Vi minus V2 divided by R1. So R1, just shifting it, R1 is equal to Vi minus Vz divided by Iz. So minimum Zener current is given by Vi minimum minus of Vz divided by R1. So maximum Zener current Iz maximum is given by Vi max minus of Vz divided by R1. So total power dissipated in R1 is given by PR1 is equal to Iz square R1. This is a total power dissipated here. So when we want a Zener minimum current, we use this formula. When we want a maximum current, we use this formula. Coming into a problem. So we came into the end of the module. So we will discuss the problem now. So first problem is calculate the forward and reverse resistance offered by a silicon diode with the given data. So they have given what is VF, IF, VR and IR. We need to find out what is RF and RR. So we know the formula. RF is given by VF by IF. So VF they have given, just substitute the values here. When you substitute the values, you'll get 7.5 ohm. So same way, we have a VR as 50 volts, IR as 100 nanoamp. So what we do, RR is given by VR by IR. Just substitute the value and calculate the value here. So nano means 10 to the power of minus 9. That you need to know. Milli, man, nano and all. Those are the basic things which you need to know. Just substituting a value, you will get the answer. Calculate the forward resistance offered by a silicon diode with VF is equal to 30 volts, IF is equal to 60 milliamp. So RF is given by VF divided by IF. So 30 divided by 60 milliamp is nothing but 0.41 ohm. Determine the dynamic resistance of the forward current of 70 milliamp at IF. Del IF means a small change in IF is given by 60 milliamp and del VF is given by 0.025 volt. So RD is nothing but RD is given by del VF by del IF. We know what is del VF, what is del IF. Just substitute it and equate it, you will get the value. So same way, RD dash is given by, we know 26 milli, this is a formula, 26 millivolt divided by IF. We know the value of IF, substitute the IF, so equate it, you will get the value. Next, determine the dynamic resistance of a diode at 50 milliamp, forward current at IF is equal to 40 milliamp and del VF is equal to 0.035 volt. So RD, we know the formula, del VF by del IF. Just substitute the value of del VF and del IF, you will get the value. Same way, RD dash is, you have a formula 26 millivolt divided by IF, substitute the value, you will get the answer. Okay, next problem is, for the given circuit calculate the diode current assuming that diode has VF of 0.7 volts. So 15 volts, 4.7 kilo, that is given to a diode. So apply KVL to the above circuit. So when you apply the KVL, 15 volts is equal to IF into R1 plus VF. So calculate the value of IF by this, just substituting the value and note down the value what you are getting. Next, a diode with VF is equal to 0.7 volts is connected to a half wave rectifier. The load resistance is 500 ohm and AC input is 22 volts. Determine the peak voltage and peak load current and diode peak reverse voltage. So peak input is nothing but 1.414 VI. So VI is nothing but 22 volts in AC input. Substitute it, multiply the value, you will get 31.1 volt. So peak output voltage is given by VPI minus of VF. So VPI, you can just substitute the value what you have got, VPI minus of VF is nothing but 0.7 volts. It is for a silicon, so 0.7 volts. So just substitute, they have given VF is nothing but 0.7 volts. So substitute it, you will get the answer as 30.4 volts. So peak load current IP is equal to VPO divided by RL. VPO is nothing but 30.4, RL is 500 ohm. So when you substitute it, you will get 60.8 milliamp. So VPI is given by VPI. PIV is given by VPI, that is nothing but 31.1. So next is a it is about a half wave rectifier which has a 15 volts AC input, 330 ohm load resistance. Calculate the peak output voltage, peak load current, maximum reverse voltage. So we know what is VI, what is RL. So substitute the value VPI. So when you substitute it, this is a formula, standard formula. Substitute VI value, you will get 21.21. So peak output voltage is given by VPI minus of VF. So VPO is given by 20.51 volts. So peak load current is equal to VPO divided by RL. Substitute it, then you will get an answer. VPIV is nothing but VPI, as we all know, whatever the value we got for VPI, that is nothing but PIV. This is a question which you do get it for the exam. Please go through it again. You know the formula, only the values will be changed. Next, determine the peak output voltage and the current for the bridge rectifier circuit when VI is 30 volts, RL is 300 ohm and diode have VF is equal to 0.7 volts. VPI is equal to 1.414 VI. So we know what is VI is 30. So VPI is given by 42.42. So VPO is equal to VPI minus of 2 VF. Substitute the value of VPI minus of 2 VF is nothing but 0.7. So VPO is 41 volts. IP is equal to VPO by RL. Substitute the value of VPO and RL, you will get the IP value. So next is determine the peak to peak ripple voltage for half wave rectifier and filter circuit which has a 680 microfarad capacitor and the average output of 28 volts and 200 ohm load resistance and AC input frequency of 60 Hz. Given CF is equal to 680 microfarad and VO is 28 volts, RL is equal to 200 ohm. So IL is given by VO divided by RL. Substitute the value of VO and RL. T is equal to 1 divided by EF. Substitute the value. Ripple is given by IL T1 divided by C1. Substitute the value, you will get ripple voltage. So here we need to find out the ripple voltage. Just it is a very simple method. If you know the formula, you can get an answer. The last problem from this module is half wave rectifier DC power supply is to provide a 20 volts to a 500 ohm load. The peak to peak ripple voltage is not to the exceeds of 10% of average output voltage. AC input frequency is 60 Hz. Calculate the required capacitor. So T is equal to 1 divided by F. So you know what is the value of T now. So VR is equal to 10% of VO. So that is nothing but 2 volt. IL is equal to VO divided by RL. Just substitute it. So CL is equal to IL T1 RL. So by this you will get C1 value. So these are the few problems which I have solved. So you do get problems like about a resistor, finding out the resistance in the half wave rectifier, one problem. So these are the few problems which are very important. Henceforth I have solved it and I have explained it. Hope so you remember the formula properly in order to solve the problems. That is the main thing. Okay, by this we will end this session and we will continue with the module 3 in the next module 2 in the next session.